Patty. This is Mr. Potter. Recall that in our previous videos we were talking about the fundamental theorem of calculus. The idea that if I had an integral evaluated from a to x of some function f of t, which I'm integrating with respect to t, and then I promptly take the derivative of that function, I ended up with just my interior function evaluated at x. We talked a little bit about the gist of this. The idea is that when I'm looking at this integral here, this integral could be thought of as some antiderivative evaluated at my top limit minus the antiderivative evaluated at my bottom limit, which I am then taking the derivative of this expression. But keep in mind, if I'm taking the derivative of this function has this specific property. We defined f of x such that its derivative is exactly f of x. That's how we define this function. So if I'm taking the derivative of big F of x, this is just going to give me f of x. But keep in mind that I can distribute this differential operator over this parentheses, and this is a constant. This is the plus c that we get when we integrate, or some representation of it. And when I take the derivative of a constant, I end up with 0. So what happens here is that this expression ends up being very simple to solve. If I know what this function is in terms of t, all that I need to do is substitute x in for this expression, and for this independent variable, and that's my answer. So what I want to do in this video is I want to talk about some AP style questions, some of the ways that I can envision the AP asking these questions. But before I do that, I want to talk about some tweaks to this model, because there are different ways that we might see this. One of the ways that we might see this is, instead of it just being an integral from a to x of an independent function that we're taking the derivative of, we may see this as some other function up here. Not just x, but a function of x. And so what happens is, I do still want to substitute into here, but I also need to resolve this dt expression. Keep in mind, I'm really looking for the differential if t is equal to g of x, then dt would really be equal to g prime of x dx. It's almost like one of those use substitution problems that we did back in chapter 6. So the idea here is that I should end up with f evaluated at g of x times g prime of x. And this should look very familiar because this looks like the chain rule. So this idea that I can substitute x in, that is true. In reality, what I'm doing, let's go back to this, is I'm substituting x in here, but I'm also substituting x in here. And so if t is equal to x, then my differential dt is equal to dx, which for our purposes, dt dx is equal to dx dx, which is 1. So in other words, I truly was substituting a 1 in here. This really is f of x times 1. But as we do so often in algebra, we don't write when we're actually multiplying by 1. So that's one caveat that I want to kind of put here, is that if this is not just an x but a g of x, I need to treat this as if it were the chain rule. I need to take the derivative of that function and multiply times it. So that's my first tweak that I want to talk about. The second tweak that I have is I could end up with the situation where I'm taking the derivative with respect to x of an integral that goes from x to b. In other words, these limits are put in such a way that this is my constant limit, and this down here is my independent variable. And so what happens in this situation, we had the property back in section 5.3 where I can take the limits and exchange them, make this, in other words, go from b to x, as long as I'm making it a negative. And so what happens is I actually end up with negative f of t, because now my constant is down here, and so this is where the term actually becomes 0. And this is important to know because there is a third tweak that I might see. I might see that I'm supposed to be taking the derivative with respect of some integral that goes from f of x to g of x of, probably shouldn't call that f of x. Let me tweak that a bit. Let's call that, actually, let's take care of both of these real quick. Let's call this from g of x to h of x of my function f of t dt. And so there's two ways that I can think about this. One is that I just have to treat it as a normal calculus problem, where I'm going to have the antiderivative of my function evaluated at h of x minus the antiderivative of my function evaluated at g of x, and then take the derivative, and you see what's going to happen here. I get f of h of x times h prime of x minus f of g of x minus g prime of x. So that's one way that I could treat this, but there is another way that I could treat this. I could imagine that this is the derivative of the integral from a to h of x of f of t dt plus the integral from g of x to a of f of t dt. In other words, break this up into two integrals that have a common endpoint, and this common endpoint just happens to be constant. So this ends up being f of h of t times h prime of t by this gold example that we did up here, minus, because these limits are in the wrong order from the blue example over here, f of g of x times g prime of x. And so just realize that I could see it in any of these forms, and they are things that we need to be aware of. So with that being said, what I would really like to do now is I'd like to go through some examples. So I've come up with some examples of problems like you might see on the AP exam, and I want to just talk real quick about how we step through them. So in this problem, they tell us that if capital F of x is equal to the integral from 0 to x of square root of t cubed plus 1 dt, then they want to know what f prime of 2 is. Keep in mind that f prime of x would just be taking this x and substituting it n for t cubed, and of course also substituting its derivative in here. So this just ends up being root x cubed plus 1. And so once I know this definition by the fundamental theorem of calculus, then to evaluate f prime of 2, all I need to do is substitute a 2n for x. And so I've got 2 cubed plus 1, which is the square root of 9, which gives me 3. And so I'm doing the same thing on this problem down here. It's just I don't have this secondary step to do. All I'm doing is a strict substitution. This is f. I want to find big F prime. Well, big F prime is what I get when I substitute x in for t and substitute the differential dx into this dt. So I should end up with e to the negative x squared times 1. I mean, we don't usually write the 1, but I bring that up because one of their choices brings it up. They're really hoping that we're going to mess up our chain rule and take the derivative of this term. As a matter of fact, it's the error so nice that they put it twice. Down here, they're really hoping that we're going to substitute a 0 into this function as well. And that's where they're getting this choice here with this minus 1. All of these are bad. And I have no idea what's happening over here, so we'll just leave that for now. But E ends up being our best answer. And so the idea here is that we're using this fundamental theorem of calculus, but we're using it in such a way that we can answer these questions fairly simply. So I want to continue in this vein. We're going to take a look at a couple more problems on this page. And let's go ahead and blank this out. So here on this third problem, I have that the f of x is equal to this function, which of the following is false. And notice here, they're asking us, does f of 0 equal to 0? Recall that f of 0 just means that I'm going to substitute a 0 in for this top limit. So I end up with the definite integral from 0 to 0 of I don't care, because what happens when these limits are the same? I'm talking about an area under some curve starting at a point and ending at that same point, and there is no area here. It's 0. So this is a true statement, so it can't be the false one we're looking for. B says f is continuous at x for all x greater than 0. So I know that this function is continuous on the domain 0 to infinity because there are no discontinuities here. There's no place where my denominator could be equal to 0. And that's really the only thing that's going to cause problems for us on this for this function. So if the function is continuous, then the area under the curve should also be a continuous function. So choice B is true, so choice B can't be the false answer we're looking for. On C, they're asking about f of 1. And so what I want to do here, since they're asking us to evaluate the integral from 0 to 1 of 1 over root t cubed plus 2 dt. I really don't want to think of this as a calculus problem. I really want to think of this as a area problem. I want to find the area under the curve from 0 to 1. And I know that this function is positive. So I know that the height is positive. I know that my base is positive. And the product of two positive numbers is indeed positive. So this is not the false answer we're looking for. Choice D, this is where we're actually applying the fundamental theorem of calculus and why I've chosen this problem for this section. The idea here is that if f of x is equal to this, then f prime of x is what I'm going to get when I substitute x in for t. So it's going to be 1 over the square root of x cubed plus 2. And now I want to know what happens when I substitute a 1 in here. So f prime of 1 is going to be 1 over the square root of 1 cubed plus 2, which is true. So this is not the false problem that we're looking for. And that leaves this, but I want to explain why it's the false answer that we're looking for. Keep in mind that this is what happens when I substitute a negative 1 for this limit. So I'm actually trying to evaluate the integral from 0 to negative 1 of my function, the square root of t cubed plus 2 dt. And when we were talking about being continuous for all reals from 0 to infinity, in fact, it's going to be continuous on the domain as long as my denominator is not empty. In other words, from negative cubed root of 2 to infinity, which does include 1, or excuse me, does include negative 1. So this is a good point, and this is going to give me a positive function, except these limits are in the wrong order. And so in order to reverse those limits, make it an integral from negative 1 to 0 of 1 over root t cubed plus 2 dt, I have to take this negative sign out front. This gives me a positive base. This gives me a positive height, but this negative means that the whole thing should be strictly less than 0, and that's why choice E is our best answer. So this one, only one of the answer choices really use the fundamental theorem of calculus, but we had to know that fundamental theorem of calculus in order to answer this problem. Problem 4 says if cap f and f are continuous functions such that the derivative of cap f is lowercase f, then the integral from a to b of f of x is, keep in mind that this is really saying what's the area under the curve. Well, I need to evaluate my antiderivative, which we know is true from this. And I need to evaluate it at my top limit and my bottom limit. So I get f of b minus f of a, which is choice D. Please notice that if I didn't know this, I could still eliminate some of the choices. I know that I'm not going to take any function evaluated at A and subtract its evaluation at B because of the way these limits are. Not at least without sticking a negative in front of that expression, which really leads this almost to a 50-50 type situation. Is it this choice or this choice? And the idea is that if I'm trying to find the antiderivative of a function, I don't necessarily want this function. If I'm doing this, then I'm really evaluating f of b minus f of a. And that's not only true for certain values, it's not true for all values. So D ends up being the best answer here. And we're going to continue working on this. Let me go ahead and do a little bit of erasing. And we'll go ahead and scroll this down a bit. Let's take a look at problem 5. Here on problem 5, I'll erase a smidge more. What I want to do now is I want to look at this. This is really a straightforward rendition of the Fundamental Theorem of Calculus. I'm taking the derivative of an antiderivative, and so I'm going to substitute x into my function, and I'm going to substitute x into my differential, and I end up with radical 1 plus x squared. So that's easy. Not a problem at all. On the sixth problem, it says if f has a continuous derivative, then they want to know what happens when I take the antiderivative of this. This really isn't a fundamental theorem of calculus problem. It really is just a straightforward antiderivative. The idea is that if I'm doing the integral from f of x dx from some value to some other value, it's going to be equal to the antiderivative function evaluated at the top limit minus the antiderivative function evaluated at the bottom limit. Well, here the antiderivative of f prime is f. So what we're really looking for is just f of c minus f of 0. And that ends up being choice A, our best answer. So it's not really a fundamental theorem of calculus problem, because they're not saying what is f of c. If they were asking for f of c, then that would be our fundamental theorem of calculus problem. But because they're asking us to evaluate this integral, they're really asking us to do a very straightforward antiderivative substitution. So let's keep going. 3 more problems that we need to do, and then we'll be done. So let's go ahead and take a look at what we got. So in this problem, it says for all x greater than 1, and we'll see why they specify this in just a moment. If f of x is equal to the antiderivative of this function, what is f prime? Well, I know that f prime is going to be the derivative of this antiderivative from 1 to x of 1 over t dt. And they specify this x is greater than 1 for 2 reasons. One is if x is equal to 1, then I run into the problem that the integral is 0. And if x is less than 1, then I run into the problem where these are in the incorrect order. But the other reason is the antiderivative of this actually ends up being natural log. And substituting values that are negative into natural log could be troublesome. But I'm never actually substituting into a natural log function because of the fundamental theorem of calculus. I'm substituting x into my function, and I'm substituting the differential into here. So I end up with 1 over x times 1. But of course, we never write that 1. B is our best answer. Problem 8. This is one of our tweaks. Because it's not just x here. It's x cubed, or x squared. So what we need to do is we need to take this x squared and substitute it both here and here in order to find f prime, which is the derivative with respect to x of this. Of 1 plus t cubed dt. So when I substitute x cubed into this, I end up with the radical 1 plus x squared cubed, which is really 1 plus x to the 6th. But when I substitute into the differential, if t equals x squared, then dt dx is really equal to 2x. So I need to take this expression and multiply by 2x. And that makes b here our best answer. So this is where we had to do that tweak that we discussed. The idea is that if this is really some function g of x, then I need to substitute g of x in here and find its differential as well. And the last problem I have here, it's very straightforward, but the reason I have it is because it doesn't involve t. And a lot of people get stuck that if a problem has to be in exact format, the independent variable has to be t, my function that I'm substituting in has to be x, and it doesn't. It really doesn't. This could be a t, it could be a u, it could be a z, it could be a q, this could be an m, this could be an r. It really doesn't matter what letters we're choosing, but it's the idea that I'm taking the derivative, and this needs to match this, and this needs to match this. That's what's important. So I'm taking the derivative of an antiderivative. I'm substituting into the independent variable, and because I'm integrating with respect to u, I know my independent variable is that u. So I end up with cosine of 2 pi x times 1. And so choice D ends up being a beautiful answer. So I wanted to go through some examples of how the AP would ask these questions if they were to show up on the AP exam. Because these types of questions are rather important to understand. These are wonderful examples of applying the fundamental theorem of calculus. The idea that if I take the derivative of an antiderivative from any constant to an x of f evaluated at some separate independent variable, I end up with just f of x. So once again, this is Mr. Potter. Thank you for watching. Have a great day.